Hello again. I'd like to do another molecule in MolCalc, which is also a greenhouse gas. And a lot of people don't realize it's a greenhouse gas, but it's actually the most important greenhouse gas, namely water. And I'll show you why. Of course, there's a lot of water in the atmosphere, and let's create water. So we again have methane as a starting material. So I'm going to take this carbon and make it into an oxygen, and right away we have water. Okay, whoops. Let's see. We got two waters, so let's see if we can delete one of them. There we go. So now we have water, and let's optimize it as we did before. And again, you can do all kinds of things with this program, measure bond lengths and bond angles. And now, water is a polar molecule. It has a dipole moment. Oxygen is more electronegative than hydrogen, so this bond is polar and this bond is polar. So let's calculate the properties of water. And again, we're mainly interested in vibrations. Again, I urge you to play around with this program. I think those of you who are faculty, teachers can learn a lot about, use it as a valuable tool for your students. So let's calculate the vibrational frequencies as we did for carbon dioxide. Now, water has various ways in which it can, these motions, by the way, are exaggerated. Okay, so there's three frequencies. The number of modes of vibration, by the way, are for a nonlinear molecule, it's 3n minus 6, and for a linear molecule, it's 3n minus 5. So carbon dioxide, being linear, had 3 times 3 is 9 minus 5, because it's linear, which is 4. One of them, the lowest frequency one, was degenerate, so that it had two vibrations of the same frequency. This is 3n minus 6, which is 3. So the lowest frequency one is a bending motion, as you can see. Obviously, it doesn't bend. There's a little bit of stretching associated with that motion too, by the way, but it's mostly a bending type motion. And because the molecule is polar and it's changing its structure, there's an oscillating dipole associated with this, so it's infrared active. And so if you were to figure out what the frequency, the wavelength of this is, when light has a wavelength associated with 1,742, again, these are calculated. The true experimental ones are a little different, but roughly 1,742 waves per centimeter. That wavelength is in the infrared region. And the Earth emits some radiation of that wavelength, and some of that will be absorbed by water. And now let's look at the second one. And this is called an asymmetric stretch. Again, greatly over-exaggerated. I wish maybe there's a way of changing it, but it doesn't have those large amplitudes. But that is infrared active as well. The dipole moment is changing because the polarity of the bonds are changing. The two bond poles change as the molecule vibrates. And finally, we have the symmetric stretch, again greatly exaggerated, at almost 4,000 wave numbers. And light of that particular wavelength, again, the experimental value will be a little different, 3,989 waves per centimeter will, whatever that wavelength is, will be absorbed by water. And water is a greenhouse gas. Or if you ever go, let's say, traveling in the West, at nighttime, it's very dry in some places, and there's not much water in the atmosphere, and so most of the radiation that the Earth emits during the nighttime passes right through out into space because there's not much to absorb it. Whereas on a humid night, a lot of that radiation will be trapped, and it will keep the Earth warm. So there's another example of MolCalc, and again, I urge you to get it off the web. Just do a Google search for MolCalc or the molecular calculator, and I think you'll find it to be a very useful program if you're a student or if you're a teacher. Thank you for your attention, and I'll see you next time.